Okay, so now we're going to get going with some problems, right? Specifically, we're going to think back to the firework puzzle and execute it as a quantum circuit, okay? So I think before we hop into this, I want to make sure that everybody has access to their module 6, because this, this is going to be everybody working on this problem. So let me just, make sure everyone navigates to their module 6, and you'll find the example code blocks to fill in at the very end. So this will be at the very bottom of your module 6, right? And then I'm going to have module 5 pulled up so that we can have some good visuals on the puzzle again. Yep. Right. So I think it might be useful to review what exactly we are trying to construct in this problem together, give everybody some time to think about what gates that they would add, in what order, what is the, how does everything correspond, and then we'll go through and we will write them up together. So that's the current plan. So let's just review the solution to the puzzle, right? So each beam splitter, right, we said acts as a Hadamard gate, right? And the trick is that this Hadamard gate treats, the two possible states of the system, in this case the photon, the way that it's coming in, differently. So if it's coming in from the left, it takes it to an equal superposition of having been reflected and having continued, and that has a positive sign. And when it comes up, instead, you get the same, either reflected or transmitted with a minus sign. And what that does is it allows for the interference up here, right? But stepping back and thinking about what are the logical states, right? These mirrors here aren't doing anything except redirecting it. So they're not affecting the state of the photon as far as the beam splitter is concerned. So all that's happening is a photon is coming in, definitely moving to the right, being put in equal superposition of being deflected upwards or continuing to go to the right. So those are our two distinct states, right? We have the 0 state corresponding to moving in this direction, and the 1 state having been reflected and now moving in the up state. So if we keep going, all that this reflection does, it doesn't change that the state is having continued on this path, right? And so really it's not going right and going up, it's bottom path as a state and up path as a state. Okay. So in that case, these beam splitters act exactly as Hadamard gates, right? And as we kind of saw before, Hadamard gate undoes itself if it's immediately sequential, right? And so if there were no box here, having a photon go in, hit a beam splitter, be put in that equal superposition, and then have the exact same operation, it's as if these beam splitters aren't even there, right? In that case, the photon goes, hits the mirror, and hits detector, right? So when you're thinking about this in terms of a quantum circuit, you were thinking about a qubit, right, which has one of two states. And you'll consider the 0 state to be the bottom path, and traveling on the bottom path, and the 1 state being traveling on the top path. And you want to reconstruct this situation, right? And there are 3 cases. One in which there was no firework, one in which there was a firework and it explodes, and the last that there was a firework, but that it was measured to be on the non-firework path. So I just kind of wanted to reiterate that so we can see the parallels and hopefully make it a little bit less abstract. Precisely, the 0 state is the top, well, I guess at right, yeah, this is the top path, up then right, and then this is the bottom path. So I guess in my description, I had that the other way around, but it doesn't really matter. Right? The point is that these are the two distinctions. So, you know, if that helps. But anyway, so, yep, measuring the state is analogous to which detector it hit. So if it were to take the bottom path and there were no beam splitter, you would hit detector. And if it took the top path and there were no beam splitter, you would hit detector B. So this is the equivalent, this is the same as just a qubit, right? And the result that it could possibly be. And so first we want to construct a circuit, right, which recreates this behavior if there was no firework. We'll give a few minutes for that. And so to remind everybody, the way that you add gates, right, is circ dot the gate that you want to add. And in this case, because we only have one qubit, and you add them sequentially by putting them right after each other. Okay. And so when someone has, you know, constructed their circuit in this section right here and would like to share, I either post the gates in the chat or just say that you have a suggestion. Right. So what outcome do we expect from this result? Right. Well, it undoes itself. Right. So we've got, you know, the circuit is always going to initialize in the 0 state, and so 1,024 times all shots we measure precisely the same state, right? 0 state. And so that's as if the beam splitter wasn't existing, and that's kind of what I was talking through. In this case, the 0 state is the path that the photon gets started on, right? Which is always, you know, this bottom path. So if there are no beam splitter, then, you know, there's no opportunity for the photon to get deflected or be measured over at detector B. And so we 100% of the time we're going to see, we're going to measure that it took the bottom path, and we know that because it ended up at the detector on the bottom path, or on the trajectory from the bottom path. Okay, so now we're getting into the firework presence. Okay, so how does this change things? What is different in the case that we have the firework on the bottom path? That's right. So the state of the photon is 0. Label it 0 if it's on the bottom path, and label the state of the photon as 1 if it is on the top path. Yeah. That is the interpretation. So what is the circuit that is happening? Okay, so we have H, X, H. Okay, so that's our first submission. Let's go for it. Okay, and so what does this correspond to, right? Well, we have our beam splitters, that's for sure. So we're getting, you know, getting put into our superposition of bottom path and top path. So what is this X gate doing? Oh, so it's swapping values, exactly, right? It's you know, whatever the state of the qubit is, it swaps the 0 and 1 in the superposition, right? So if it's in the pure 0 state, then we know that it acts as, it flips it to a 1. And if it's in the pure 1 state, it flips it to a 0. But in this case, the X gate is happening after we've placed the qubit in superposition, right? And this is actually something that we weren't planning on dissecting here. But I will say that this is not the answer that I was looking for. But does anyone want to say what they think will happen with this circuit? Don't know how to model the different path. No, that's totally fair. So so just reviewing. So in the case of a firework, right? You know, this is what we want to simulate happening. It's not so much that we're worried about, you know, this being put in, you know, maybe taking a different path. We're saying that we're measuring whether or not, like which path it's on, right? And yes, by the way, the circuit HXH would 100% of the time result in 0. And the reason for that, you know, in a precise way, the X gate doesn't do anything to the superposition state that we've fed into it. And that's a concept that is pretty important. Which states does the gate do nothing to is a very important question, but won't get into that. But I hope it's cool to see that you can, you know, would you look at that? This is a circuit that does the same thing as anyway. So yeah, so what we're looking for is a measurement in between our two beam splitters, right? Exactly, Lorraine. So we want to measure, right? And ideally, we would have something like, you know, like so once we execute it, you know, maybe we execute it once and then we say, you know, if result, you know, dot counts or something is 1, print the firework has exploded, right? But the circuit that we're interested in, right? Oops. Missing classical bit. Right. Oh, is that better? Yeah, in this case, we're you know, measuring the path, right, which is the state of this qubit, the state of this photon, right? And you would want an if statement to say like this is exploded in whatever case. In this case, we're measuring a 0, which means bottom path, which means this should explode, right? Okay, great. And so you can imagine then we've arrived at the answer for the last case as well, right? So if 0, once we measure the value is set. Yes, absolutely. So once you measure at this intermediary step, right, the photon has to choose what path it's on in a way, right? This superposition that was created by the beam splitter is destroyed. It's collapsed into a classical state. You know, it's still a quantum state, but in the quantum state is with probability 1 on the bottom or top path at that point. Yep. And so that's why we would record the value of this intermediary measurement, right, as a classical bit, and then you could say, if this happened, then stop the circuit and print a statement saying that the firework has exploded. If that measurement is a 0, right, what happens then? Or if that measurement is a 1, oops. So I've been saying, so I don't confuse the notation here, I've been saying that the bottom path is 0. So if it is a 0, print, you know, stop the circuit, print a statement that the firework has exploded. If it is a 1, though, what happens? Then apply another Hadamard gate and measure. Yep, exactly. Yeah, and so that's how we see that, you know, when the photon goes on the upper path, it is not in a superposition anymore, right? It is in the pure top path state. And when it reaches this beam splitter, now it gets put into equal superposition, just like it did the first time, right? Going from pure bottom path state, right? And then it will split 50-50, exactly. Right. Yeah, so here we're seeing, in the case where it gets measured when the superposition, positions you could think about it are here, it's now definitely on the top path. And half the time, the superposition at the detectors is collapsed into A, and half the time is collapsed into B. And why is this, whole setup just a single qubit? Well, because at every step of the way, we're only distinguishing between two possible states of a property of the photon, right? It's either going this way, in which case, without the beam splitters being present, it hits detector B. So that's the measuring of being in the top path. And at any point, without the beam splitters, if it was on the bottom path, it would hit detector A. That is a detection of that state, right? Cool. And so, I think that roughly covers it. I hope that was worthwhile, so that we finally we've got a nice little bow on our firework puzzle, and how this really is equivalent to a quantum circuit that does not have a classical analog here. Okay, and so I think that's everything that I have for my session.